Okie dokie. Hello everyone. Today we're going to go through paper C of the IYGB papers. So I've done A and B the last couple of days, so we'll have a go at number C today. So these are A-level papers, a little bit harder than the standard ones generally, but it seems to be that as we go through the alphabet, they're going to slowly get harder and harder. So what do we start with today? So the figure above shows curve of the equation x squared minus 4x plus 10. Find the area of the region bounded by the curve, the coordinate axis and the straight line with equation x equals 3. You see this shaded area. We just want the entire area underneath the graph here. So to do that, we need to integrate, and we'll integrate with respect to 0 and with respect to x, but between 0 and the 3 that we have. So integration from 0 to 3 of the x squared minus 4x plus the 10, that's not very good, 10, plus the 10 dx. So the x squared, we'll raise the power, make that into x cubed, divide by that new power of 3. For the 4x, raise the power to 2, and then we'll divide 4 by 2 to give us a 2. And the 10, we'll raise the power. You can imagine this as being like 10 lots of x to the power 0. So raising the power, we'll get x to the power 1, divide by that new power of 1, gives us just 10x. And then we need to sub in the values of 3 and of 0. When we've got 0 as one of the limits of our integration, and we have just a polynomial thing, every single thing here is proportional to x. So whenever we plug in 0, all of them are just going to become 0, because 0 cubed, 0 squared, and 0 are all 0. So any multiples of those that we have, will also be 0. So all we need to do, plug in the 3. For the x cubed, you can think we'll have 3 cubed, divided by 3 is 3 squared, which is 9. 3 squared again is 9, but take away 2 times that, so take away 18. And then 10 times 3 is 30, so adding that on. So altogether, what do we have? This is minus 9, this is plus 30, 20. So 30 take away 9 gives us a total answer of 21. Lovely jubbly. Let's keep going. So here we have another quadratic, 2x squared minus 9x plus 4. We're going to sketch the graph. We must include the coordinates of any points where the graph meets the coordinate axes. So to do that, we need to factorise. So to do that, we can kind of assume that everything's going to be made from integers. We can start there. We can't really assume it, but if we start there and just kind of imagine it's going to happen, we can see if it works, it works. If not, then we can try a more complicated method. But often it's a bit quicker just to kind of like trial and error and see if it's going to work. So that 2x squared, it must come from, with the two brackets, one that's 2x and one that's a single x. And this 4 can either come from 1 and 4 or 2 and 2. Could be 4 and 1, but the same sort of idea. So then we need to think about the combinations that can happen. We need to make a 9. So 9 would be nice if the 4 went with the 2 to make an 8, and the x went with a 1 to make a 1. So that's going to be what's happening here. We need a minus 9. So both of these are going to be minus. And like we said, we want the 4 to go with the 2x. So when the brackets get expanded, everything from this bracket is multiplied by everything from the other bracket. So we need that 2 and that 4 in opposite brackets. So that'd be x minus 4 over there, and then put the 1 on this side, and we can just double check. So this will give us minus 8x. This gives us then another minus x, so minus 9 altogether. And the minus 4 and the minus 1, so minus 1 and minus 4, give us a positive 4. So this should be our factorised form. So if we imagine this equal to 0, what we can say then is that x is equal to a half and also 4. And then we have the y-intercept of the positive 4. Because I think if we did summing 0 into f of x, we'll end up with that just equal to 4. Namely, the same idea from the last question. These bits are polynomial parts. Anytime we plug in 0 into any of them, we get 0 back on the other side. So from here, we know that we have these coordinates of a half and 0. We're going to have 4 and 0, and 0 and 4. That's just coincidence. Doesn't always happen like that. It does happen quite often though, because like the 4 over here is obviously the y-intercept, and these numbers have to be multiples, factors of 4. So sometimes you do see the same number appearing for both the y-intercept and the next intercept. So as we draw this, we have a positive quadratic. At some point, it's going to cross an axis, and that's going to happen. Let's use this little black line as that line. So we're going to have here can be a half, here can be 4. So you can see that the y-axis should be over here somewhere. Let me just turn that into black so it matches the other one. And then this line up here is going to be 4 as well. So that should be the entire sketch of the graph that we need. So when is this positive? Well, we can see kind of in 3 different regions. Like when it equals 0, it's positive on the outside here and then negative on the inside. So we want to have those 2 outside regions. So x is going to be less than a half, or x is bigger than 4. Note that you can't say and in there. If we said when it's x is less than a half and x is bigger than 4, that can never be true at the same time, because you can't be smaller than a half and bigger than 4 together. So the and here is not going to work. It has to be or. It's like the union of these two regions, one on either side. Lovely jubbly. And just to note as well, we don't have like an equal to part in here. It's just strictly greater than 0. So we're basically matching. If this had greater than or equal to, these would both have an equal to part in them as well, because we would be allowed to have the value of 4 and the value of a half. But in this case, not allowed those bits. Spot on. We'll keep going. Number 3. What do we have here? So we've got some big box, X, and then H on the axes there. The figure above shows the design of a large water tank in the shape of a cuboid with a square base and no top. The square base is length x meters and its height is h meters. It's given that the volume of the tank is 500. So the surface area of the tank is given by this thing. So these sort of questions are quite common. We have 2 different measurements. We have the volume and we have the surface area. Let's think about the formula for both of those. So for a cuboid, the volume is just all the sides times together. So in this case, x squared h. And the surface area, we need to work out the area of all of the sides and add them all up. All of these vertical sides have one length of h and the other side of x. We have 4 of them. So we're going to have 4 times by x times by h, and then plus the base of the x squared that we have. Note that if this was like a closed cuboid, this would be 2x squared for the top and the bottom of the cuboid there. So that's good. We want to use these then. We know that the volume of the tank is 500. So this x squared h must equal 500. And then if we look at the actual thing we're looking for at the end, there's no h in there. So we want to take this expression, rearrange it for h. So we'll get the h is 500 over x squared. And then we can take this value for h and substitute it into our expression for the surface area. So what we get from that, the surface area then, is 4x times by h. So 4x times this. The 4 and the 500 will make 2,000, which you can see as part of the answer down there. That's a good sign. We've got an x squared on the bottom and an x on the top. So that's going to give us a single x on the bottom. So exactly what they've got in the bit down there. And just want to add on the x squared that we had originally as well. Spot on, that's all good. We want to find the value for x for which a is stationary. So to do that, we need to differentiate. It's always probably worth writing everything in index form first. So the 2,000 over x, we can think over x is the same as x to the power of minus 1. So when we go to differentiate this now, so d of SA over dx, what do we get from that? Well, we need to times the coefficient by the power. So the 2,000 and the minus 1 times together to give us minus 2,000, and then lower that power by 1. So the minus 1 will drop down to minus 2. The x squared, nice and straightforward. Again, bring that power to the front, makes it a 2. Drop the power down to 1. So we have just 2x over there. When we're looking for stationary points, what that tells us, well, how we do that is we know that dy dx should be equal to 0. So in this case, the rate of change of the surface area should be equal to 0 as well. So we can do that. And now we want to solve this part of the equation. So let's first of all add this over to the other side and divide by 2. So we're going to have 1,000 over x squared is equal to a single x. We can then go and times by the x squared. So 1,000 will equal x cubed. And then divide, well, not divide, do the cube root on both sides. So x should equal just 10 for that one. Lovely jubbly, circle that bit too. And then part C of this question is to find, well, to justify that it is a minimum part. So to do that, we need the second derivative. So we want d2sa over dx. To do that then, we differentiate this again. What's going to happen then? The minus 2000 and the minus 2 will make positive 4000. The power again will drop from minus 2 to minus 3. And the 2x will become just 2. So we can look here, if you want to, you can just plug in x. So I think if we do that, it's probably the easiest way. So that tells us d2sa over dx squared is equal to 4000 over 10 cubed. 10 cubed is 1000. 4000 over 1000 is 4. Plus the 2 gives us 6. That is positive. Therefore, we were at a minimum. You can be a little bit smart and think over here. Basically, anytime your x is positive, x cubed is going to be positive. 1 over something positive is also positive. 2 positives times together is positive. 2 positives added together is positive. So you can kind of work it from there and just show that it's always positive if x is positive. But it's easier sometimes just to plug in the number instead. Lovely jubbly. So if any questions about this sort of stuff, give me a shout in the comments or in the chat. So here, question number 4. We want to solve in degrees the following trig equation. So we've got tan of 3x minus 75 is equal to tan of 450. So tan of 450, that's just a number. So when we go and think about that, what are we going to get? So think tan of 450, you can take 360, it's tan of 90. When we go and actually do tan of 90, not allowed. Same idea, tan of 450, not allowed. So it's basically having the idea that this is not, it's infinity, but we can't really say it's equal to infinity. But we want to find basically at all the points when this is going to have an asymptote between 300 and 500. So to do that, what we'll first do is think about the fact that we can kind of rearrange this, not rearrange it, but rearrange the domain so that our x, we're going to manipulate that to form 3x minus 75. So let's triple it. We'll get 900. It's less than or equal to 3x, which is less than 1,500. And then we will take away 75 from all three sides there. So we're going to have 825 is less than or equal to 3x minus 75, which is less than 1425. So that's our kind of new domain that we're going to work with. So we want to find answers for now just a general kind of thing of tan y, if I can write y correctly, is equal to tan 450. Or you can think of it as equal to infinity. Should never be equal to infinity, but it's kind of not a bad way to think about it. When does that happen? That would tell us it's every like 90 or 270 or 450. So in that case, y is going to be 90 plus 180n. And we want to now find every single value of this that's in our range from 820 to 1425. So to do that, we'll just keep chugging in values of n. So we can think here, this is going to give us, like I said, 90, 270, 450. The next one will be, if I can do the maths in my head. So we're taking away, it's going to be something 30, 630. And then it will go to 810. And then it's going to go to 990. Adding on another 180, we're going to get 1170. Another one, we will get 1350. And the next one then is going to bring us to 1530. So now you can see this one is too big. This one is too small. So we're left with 3 that satisfy our range from 825 to 1425. So therefore, we can take that and set them all equal to the 3x minus the 75. So 3x minus 75 is equal to 990, 1170, and 1350. So add the 75 to all of these. That will give us 1065. We'll have 45 left over here, so 1245. And then this one's going to give us 1425. And then we divide all of these by 3. I won't do that in my head. But if we do the 1065 divided by 3, we get 335. Then the 1245 divided by 3 gives us 415. I'll give myself a bit more room. 415. And then 1425 divided by 3 is 475. So you can see, like, where we manipulated the domain, we were able to just solve it as if it was just tan of y is equal to this stuff, and like y was equal to 3x minus 75. We didn't need to write all these out, but you can just like check in the calculator, see which ones actually satisfy it. But because we manipulated the range, we didn't have to worry about anything strange about the repetition of tan. So tan repeats every 180. Here we just did 180 stuff. If you've got, say we didn't manipulate the range and we did the same sort of ideas, we'd have to add on 60. So the 180 divided by the 3 in here. This works for when it's a linear thing in here. But if you ever go forward and do other more complicated maths where this is not a linear thing, it gets a bit messy because it's not like a constant change. So I think it's always worth kind of manipulating your domain, finding the answers normally, and then just subbing back in and solving the kind of linear equation, or whatever equation you get is equal to all your answers. So here we get 3 different answers, and that should be good. If you think here, this is 200, it's roughly 180, just a little bit bigger, but it happens 3 times. So we should get 1, 2, 3 different answers in there. Lovely jubbly. Let's keep going to number 5. So what have we got now? Some circle. The figure above shows a circle that crosses the x-axis at the points A, which is -1 and 0. That's down there. B is 7 and 0. And it passes through point C, which is 3, 8. Determine the coordinates of the centre of the circle and the length of its radius. Okay, so this is quite a long-winded idea. In general, this is what we need to do. We're going to draw lines connecting 2 of like the pairs. So like, we've already got the line AB, that's nice. We can connect the lines AC then, I'll do this in blue. Yeah, we can connect these 2 up and connect AB up. We could connect BC as well, but we don't kind of need all 3 of them. And then from there, if we find the midpoints of all of these and draw tangents from those, so perpendicular lines coming up from those points, what we'll see is that they should cross over at the exact centre of the circle. So this bit should be the centre. So what we need to do is go through and find all of these points. This line then, I will start labelling things. So we'll call, this can be line AB, and this can be line AC. And the other 2 then, this can be, we'll just call this L1, and this can be L2. So when we think about what's going on, AB we already know. AB is nice and straightforward. It's just the line that y equals 0. And the midpoint then, this was -1 at A, 7 at B. So this midpoint should happen at 3, right in the centre over there. And then what do we have for the line L1? L1 is definitely going to equal x is equal to 3. So that's exactly what L1 is, nice and straightforward. Be a little bit more complicated for L2. The first step, let's find what AC is. So to find AC, we need to find, first of all, the gradient and the y-intercept. So for the gradient, we need to do the difference in y's over the difference in x's. So using the point C, we'll have 8 and a 3. And the point A, we will have a 0 for the y's. And it'll be minus 1. So that is positive 1 altogether. So we have a gradient of 8 over 4, which is 2. And you can think what the gradient represents is how many up steps you take for every 1 step to the right. We're going across from -1 to 3. And we're going to go up by 8. So you can think like we're going to cross 4 up by 8. So that is every 2. We're taking 2 steps every time we take 1 step to the right. Just notice, yeah, this 3 8 should be above here. I'm happy with my diagram, but like this L1 does actually like intersect with this. So these 2 points should intersect over here. Maybe that's a way that we could do a shortcut, but I've started now, so I will carry on doing this way around. So what we have now, y is equal to 2x plus c. We then just need to find those coordinates. Well, we've got a on the line, so if we plug in the coordinates of a, we can solve that for c. So the y value is 0, the x value is -1, 2 times -1 is -2, still plus the c. So c is equal to 2. So the line AC, altogether, y is 2x plus 2. Let's find the midpoint then of that line AC. So to do that, we're going to add, and we'll do the average basically of A and C. So to do that, we'll have the 3 plus the minus 1 over 2, and the 8 plus a 0 over 2. What does that give us? For the first one, we have a 2 on the top, 2 on the bottom, so we get a 1 altogether. And for the second one, we have 8 on the top, 2 on the bottom, so we will get a 4 when we combine that. So that tells us that this midpoint over here, this point right here, the one in there, has those coordinates of the 1 and the 4. Now then, we can use that 1, 4 and the fact that L2 and AC are perpendicular. So when we go and look at L2, what we're going to have is its gradient must be the negative reciprocal of AC. So y is equal to not 2, but negative 1 over 2 times by x, all plus c still. Next is a different c to what we've got over here, nothing to do with that, and as well to the symbol, to the point even. So let's do a similar idea. We know it goes through 1, 4. Let's plug in 1, 4 to this. So we'll have 4 is equal to a half of 1, so negative a half of 1, which is minus 1, plus the c. So c is equal to 5 in that case. So L2 altogether, y is minus a half of x plus 5. So now we have L2, we have L1, we want to find where they intersect. L1 itself is quite simple, just x being 3. So all we need to do, plug in x is 3 into there. What does that give us? We'll have y is minus a half of 3, so minus 3 halves, plus the 5. So doing that, 5 is 10 halves. 10 take 3 is 7. So this is 7 halves. So the centre as a coordinate is going to be the point x is 3, y 7 over 2. And that should be, the final answer for the centre. We also need to find the radius. So to do that, we can use any of the points that we have, A, B or C. Probably easier to use like A and B because they've got y values of 0. And I'll go with B because it's got a positive coordinate. So we need to find then the difference from the centre to B, sorry. So right now we're at 3, we need to go to 7. So that's got a gap of 4. And for the y coordinates, this is at 7 over 2, this is at 0. So the difference is 7 over 2. And to do this then, what we've basically found is this triangle, where the hypotenuse of this right angle triangle is the radius. So we want to use those two values with Pythagoras. So it's 4 squared plus the 7.5, so 7 halves all squared will equal r squared. So expanding everything out here, 4 squared is 16, plus we'll have 49 over 4 for 7 over 2 squared, still equal to r squared. The 16, if we write that over 4, we can think about just timesing it by 4 to get 64 over 4, and then plus the 49 over 4, still equals r squared. And now then, the 64 plus the 9, and we don't need that equals there. Yeah, 64 plus the 49 is going to give us a number of 113, still over the 4. And now then, when we square root, we'll have the square root of 113 on the top, and a square root of 4 on the bottom, which is 2, not just a dash. Yeah, so that's the radius, 113, or root 113 over 2, and the centre is 3 and 7 over 2. Lovely jubbly. Let's keep going. We have some water quick, and then we'll keep going. So question 6. We have y is equal to 2 to the power of 3x. And describe the single transformation, or geometric transformation, which maps the graph of y equals 2 to the power of 3x to the graph of 2 to the power of 3x plus 4. There's two different ways you can do this. Either we can take the 2 to the 3x plus 4 and factorise that 3x plus 4. So let's take the 3 out. We still have the 2 up there. Take the 3 out, and it will be x plus 4 over 3. So this then is referring to a translation to the left by 4 over 3, which you can write as a vector. So this will be a translation through negative 4/3 and 0. So this is saying it's just going horizontally left by 4/3, up and down by 0. The other way is to use kind of your power laws. So the 2 to the power 3x plus 4, you can split into 2 to the power 4 and 2 to the power 3x. That 2 to the power 4 is 16. Let's move this over a little bit. So it's 16 times by 2 to the 3x. So that is going to change it as, like, again, we're going to have an enlargement of 16 vertically. So it's an enlargement. And again, we can do a vector. Horizontally it's 0, vertically 16. So either this or this would give you all the marks for part A there. Oh, and looking at part B, yeah, describe a different transformation which maps the graph of this. So yeah, we've done part B already. So you can see the two different transformations, both not too bad to figure out. Basically, you're looking for, can you just remake the original function over here? And yeah, we were able to extract this out and just have everything else kind of working on that, just applying itself to that part. Or can you kind of isolate a bracket that would look like the x in the original one? So this whole bracket now looks like the x in there. And in that case, then you can just think, okay, x has become x plus 4/3, which is a translation, yeah, to the left by 4/3. It's not too bad, that one. Nice and quick, simple one. We'll keep going to number 7. We want to prove by exhaustion that if n is a positive integer, that it's not divisible by 3, then n squared minus 1 is divisible by 3. So doing it by exhaustion, what that means is that you try all the cases. So when we've got something that is not divisible by 3, what we can say is that n is either 3k plus 1, or it's going to be 3k minus 1. We could be really fancy and do it's 3k plus or minus 1, where k is going to be any integer that we're allowed. So in this case, we need it to be a positive integer. So we can go through and just say that k then has to be also a positive integer, i.e. a natural number. Just double checking, so the smallest one is 1. Does this actually give us all the numbers that we need? So the smallest is 1, so this would be 3 plus 1 is 4. 3 minus 1 is 2. So the only number we need to double check is 1 as well. But we can see 1 squared, so yeah, let's check 1. So let's check 1. Check n equals 1. N squared minus 1 would be 1 squared minus 1, which would be 0, which is equal to 3 times 0. So therefore it's true. Let's write that down. So therefore true. When we go and check n is equal to 3k plus or minus 1, what's going to happen then is we'll have 3k plus or minus 1 all squared. Take away 1. Expanding that bracket. In both cases, we'll have 9k squared. We will get some form of 6k. For the positive one, it'll be positive. For the negative one, it'll be negative. So plus or minus 6k. And in both cases, again, we'll have a positive 1 at the end. Take away that 1. So just cancel those 1s out. We will have 9k squared plus or minus 6k. This then, 9 and 6, both multiples of 3. So let's factorise a 3 at the front. So 3 lots of 3k squared plus or minus 2k. This evidently is something that's a multiple of 3, because in here, all the k's are integers. Squaring an integer is still an integer. If we like triple or double an integer, still an integer. And then adding them or subtracting them, still an integer. So this whole thing is an integer, so it's 3 times something. So that should be all good to rock and roll. Lovely jubbly. Let's go to number 8. So we've got a big table of data here. What's it saying? A financial advisor wants to model the annual growth of certain investment based on the growth of this investment in the past 7 years. So here we've got the value in thousands, increasing on 1, and the years on the top. He assumes this formula is true, where R represents the constant annual percentage growth. So this is just, this is like compound interest formula. Looks a bit strange here, but you can think, imagine R is 2. You're gaining 2% a year. This would become 1 plus 2 over 100. So 1 plus 0.02, which is 1.02. So gaining 2%, and you just keep times it by that number to grow. So yeah, R is the constant annual percentage growth. N is the number of full years elapsed at the start of the investment. State the initial value of this investment. Looking at that, when we plug in N as 0, this whole bracket, anything to the power of 0 is 1. So the entire bracket, including the N, becomes just 1. So initial value should be 40. Whenever you see the word state, generally there's no maths to do. You should be able to see the number on the page, or it's a very simple, like, add two numbers together, add one number together, something like that. Part B then, show the data is consistent with his assumption using a graphical method involving logs. Okay, so I had a question like this in paper B yesterday. Let's take our expression. V is 40, 1 plus R over 100, all to the power of n. And let's take the log of both sides. Natural log will do. Doesn't say which log to do, but yeah, we'll do natural log. So natural log of V will be the natural log of all of this stuff. And now we can use the log laws to expand the one on the right. So let's just move this over here so I've got a bit more space to work with. So we've got log of two things times together. So they'll become added together as logs. And now the power on this second one is going to come down to the front. So instead of being a power inside the log, it's going to be a multiple of the log. So log 40 just comes with us, plus n times the log of 1 plus r over 100. So yeah, again, this being like the scale factor per year, effectively. So looking at this, we still have the log v. This forms a straight line then. This basically always happens with exponential graphs. You can transform them by using logs into something that is a straight line graph. And now we just want to plot these values. So we need to have log v, that will be our y. The log 40 will be the c. And then we're going to add on what is like our normal kind of x value. Think of like the x-axis is going to be the years here. So that will be x. And the gradient will be this, the log of our scale factor. So we have already our n values. We don't need the log of n, just n itself. But we do need to work out the log of all the y values. So a log of all the v values, sorry, to be our y coordinates. So let's do that quickly. We get log of 44 is 3.78. Log of 48 is 3.87. For 55, if I can type 2 5s, we get 4 on the dot pretty much, 4.01. For 63, 4.14. 67 is going to give us 4.20. 75 is 4.32. And 82 is going to be 4.41. So yeah, these are all the natural log of v, this entire row. And then in the exam, you'll probably have some graph paper or square paper or something like that. All you're going to do, take some of that graph paper. One on the x-axis, you have n. On the y-axis, you have the natural log of v. And as we go through, we should see that we end up plotting just a straight line curve, just like a straight line that goes through, starting at that like 3.78 and just slowly drawing up as we go across. So taking all of the n values as our x coordinates and all of the log v as our y coordinates should give us a complete straight line, not through the origin, but through some point over here, where actually that point we know is the natural log of 40. And the gradient should be the natural log of our scale factor, the 1 plus r over 100. So that's all good. That's for part B, showing it's consistent by using a graphical method. So that works because, yeah, we've shown the rearrangement is linear. We've shown the data we have fits into a linear pattern once we've done that rearrangement and like using the actual correct value of log v instead of just v. So you should be able to like take this and then rearrange it back into the assumption that they made with the model. So for part C, we need to determine an estimate for the annual percentage growth of this investment. Correct the two sig figs. So that's R. We want to find the R. And like I said, the gradient here is the log of 1 plus r over 100. So let's find that gradient. To do that, we'll do the difference in y's. And I won't use my graph. In the exam, I use your graph, but I obviously have not drawn that too accurately. So I will just use the coordinates I've got. So the y of the highest one was 4.4. The y of the lowest one was 3.78. The x of the highest one is 7. X of the lowest is 1. We sub that all in the calculator. What numbers do we get? So 4.4, take away 3.78. 7 minus 6 is 1. Sorry, 7 minus 1 is 6. So altogether we get that is, well, as a fraction, it is 31 over 300. So nearly a tenth. Yeah, very nearly a tenth, but not quite. So what that equals now, we have that was equal to the entire of this log bit. So the natural log of 1 plus r over 100 equals 31 over 300. And now we can go and just rearrange this for r. So let's raise both sides to the power of e. We'll have that 1 plus r over 100 is equal to e to the power of 31 over 300. Let's take 1 from both sides and times by 100. So r will be 100 lots of, give me 1 sec, get some more room there. Yeah, 100 lots of e to the 31 over 300. Take away that 1 in there. So sticking that in the calculator, we need this to 2 sig figs. So 100, open brackets, e to the power, 31 on 300, and then all take away 1. We get a number of 10.89. Is it 2 sig figs? Or is it 2 decimal points? 2 sig figs. So actually we need to round this up to 11. So yeah, rounding after the second significant figure, well, after the second figure, I suppose, to give us then, yeah, rounding up to 11. That should all be good. It's quite a good investment, yeah, 11%. That's, I wouldn't mind that if anything, I was investing maybe 11% a year. That would be quite good. So estimate the value of this investment after 10 years and briefly comment on the reliability of this estimate. So doing that, we want to basically go and plug in our 11 in here and n. Yeah, 11 is the years. Sorry, 11 is the percentage, like for r, and 10 is the years for n. So it should be that v is equal to the 40, 1 plus 11 over 100 to the power of 10. So doing that in the calculator quick, you can think that bracket is 1.11. So it's 40 times 1.11 to the power of 10. That gives us 113.5-ish. A little bit more than that, 113.57. Does that round up? 5.8, I suppose. How good is that? It's not too bad. Reliability of the estimate, that seems pretty good. Like, look how much it's increasing by at the minute. It's like 8 and 7 and stuff like that. So imagine 15 in 2 years. After 9 years, you'll be at 97. And then another 7. So it's a little bit of an overestimate, maybe. I think it might be decreasing slightly. So it's a slight overestimate, but it's pretty good. Maybe a slight overestimate is what I'd put here. When you're revising for any sort of stuff like this, on these questions, when it's like estimate, briefly comment, these sort of comment questions, always just make a good like guess when you're doing it. But then once you've done the actual marks, just go and have a look at the mark scheme and see exactly what words they want from you. Because a lot of these times you understand what's going on. Like that, yeah, 113.58. That seems not too realistic, like not too bad. Might be a little bit too big, but not a huge amount. But kind of what's their cutoff point for being okay and not okay? Would this be okay or would it not be okay? Generally, they make you like do an estimate for one that's inside the range you've got. So we'd estimate, like, say 5 years and see that 67 was accurate or not accurate. But here, it's outside the range. So we do need to kind of, like, extrapolate a little bit. So like I say, you can imagine, yeah, we're roughly gaining, like, it was 4, then 8, then 7. So I think that could be, like, say, 89. Add an 8, you're at 97. Add a 7, 104. So probably we're going to, in reality, we'll have a smaller number than what this predicts. But it's still, it's only like 10% off. That's not too bad. Like 10% difference over like 10 years of growth. I wouldn't be too upset if like I was overshot or undershot by 10%. Do you mean? That's pretty good. We'll keep going then. Question number 9. Here, f of x is 1 over x cubed. X can't be 0. We want to now use the formal definition of the derivative as a limit to show that f dash of x is minus 3 over x to the power 4. So to do that, we first need the actual like formal definition of the derivative. So in general, f dash of x is going to be the limit as h tends to 0 of f of x plus h. Let me slide this all over. I've got a bit more space. Take away f of x, all over h. This looks kind of horrendous if you don't know what's going on. This is just the gradient formula. Both of these are y values. One has the x coordinate of x, one has the x coordinate of x plus h. And this then is the difference in the x coordinates. I think you had x plus h, take away an x, they cancel off, all you're left with is a h. If you haven't seen much about limits themselves, basically, we want to sub in h equals 0. And we will do that as soon as it doesn't break maths. So right now, you would divide by 0. That's not allowed. We can't be doing that. So we need to do some sort of manipulation to get it so that the h is no longer on the bottom. Or at least, yeah, we're not going to be dividing by 0 at any point. So nice, that's a general form. Let's actually plug in the, the thing that we have. So f of x plus h is going to be 1 over x plus h all cubed. And we'll take away 1 plus x all cubed. Well, we'll just look at the top for a sec. One way you can do it is kind of like, we'll just have 1 over h out the front here. Deal with that in a second. So let's expand our brackets. The 1 over here is a binomial expansion. So we'll still have that 1 over h. And then we'll have x cubed. And then what's going to happen is the power of x will decrease. So squared x to the 1 and then x to the 0, which is just 1, so I won't bother writing it in there. The power of h will increase. Here was like h 0. So here we'll have h to the 1, here h squared, and here h cubed. And then the coefficients follow Pascal's triangle. So it's going to be 1, 3, 3, and a 1 at the end as well. So that's the expansion of the first bit. If we look at the second part, we still have the minus 1 over x cubed over there. So this, yeah, not hugely nice in turning into like one single fraction, but it shouldn't be the end of the world, basically. So I don't think we're going to be having the issue of dividing by 0 at the minute, which is quite nice. But yeah, let's turn this into one fraction. So we still have that 1 over h. And now, when you turn it into one fraction, you basically cross multiply. So we're going to have this bit times by the 1. So x cubed. And then take away, because we've got that take away in there, 1 times everything down here. I'll be a bit lazy, and I will just duplicate all of that stuff over there. But like I say, all of it's been taken away. So all of these positives need to turn into negatives. And this then is over the product of our two denominators. So basically, the x cubed here, the x cubed here is going to multiply all of these. So all the powers of x will just increase by 3. So we'll have x to the 6 plus 3h x to the 5 plus 3h squared x to the 4 plus h cubed x cubed. Now, some of the stuff we can start cancelling off. If we look at our top row, we have an x cubed there, it's going to go away. And now we can use our 1 over h to sub this all back in. Not sub all back in, but like cancel off one of the h's on the top row. So doing that quick, our denominator is still the same. So again, I'll use my little laziness of just copying all of this over. Duplicate. Over you go. And then yeah, everything on the top, we need to lose a power of h. So 3hx squared, get rid of the h, 3x squared. Still got the negative in front. The 3h squared x, drop one of the powers of h. And the h cubed, down to h squared. So this is good. The whole point that we've been doing here is to rearrange our expression so that we can actually perform the limit on it. So we want to be able to sub in h as 0 into the expression. We couldn't over here because we divide by 0, but now this is perfectly safe to sub it into. So as we do that, we know that the limit of all the stuff we've been doing, if I call this, let's just give it a name for a sec to make it proper. Let's shove this all over. Let's call this like z. So the limit of z is going to be just, yeah, whenever we've plugged in 0 as h. So looking on the top, just 3x squared, still negative. The minus 3hx is 0. Minus h squared will also be 0. So minus 0, minus 0. When it's like we're trying to show something, I would put in the zeros just to show that you understand exactly where the bits are all going. On the bottom then, x to the 6. And if you look kind of what we're looking for, that's a good sign. We've got the minus 3x squared over x to the 6. That will cancel off to this part in a sec. All these other bits have a h in them. So they're all going to be big, fat zeros. So altogether, minus 3x squared over x to the 6, which is equal to minus 3 over x to the 4, which is exactly what they wanted us to show. So fingers crossed that should be all correct. I don't think we made any algebra mistakes in there. But yeah, not too bad of a one to do. But kind of, if you haven't seen it done with a like power of x on the bottom yet, it works in the same way. You just expand the brackets and then just turn it into one fraction. The these bits will cancel off again, and then plug in all the zeros as you can do. So we'll keep going. Number 10. Straight line A, well, straight line number 1 passes through A, minus 4, 7, and B, 4, 9. Straight line L2 has the equation y is a half of x plus 4, and meets, so they meet each other at the point C. Firstly, find an equation for L1, find the coordinates of C. So to find the equation of a straight line, we need to find the gradient. So the gradient of line 1, difference in y's, let's do B, take away A. So 9 take away negative 7, 9 plus 7. 4 take away negative 4, 4 plus 4. 9 plus 7, 16. 4 plus 4 is 8. So this equals altogether 16 divided by 8, which is 2. So we have y is going to be 2x plus c. And now we can just sub in the coordinates of either point. I'll use b because it's positive, a bit easier to work with. So we'll have 9 is equal to 2 times 4, which is 8, plus the c. So c is equal to 1. So the full equation for line 1 is going to be 2x plus 1. So that's part A done. For part B then, we need to find when it intersects line 2. So basically simultaneous equations. We've got equation 1, well, equation 2 and equation 1. So let's set them equal to each other. So on the left hand side here, a half of x plus the is equal to 2x plus the 1. Take 1 from both sides, we'll have a 3. And then take a half of x from both sides. We'll have a 3 is equal to 3 halves. I think 2 take away 1 half. 2 is 4 halves. 4 halves take 1 half is 3 halves. So x altogether will be 2. We can double check this. Let's just plug the numbers in, make sure we get the right answer out. 2 times 2 is 4, plus 1 is 5. And then this side, half of 2 is 1, plus 4 is 5. So the coordinates of C are going to give us 2 and 5. Let's make that 5 a bit nicer though. There we go. So yeah, 2 and 5 for the intersection point. Straight line L3 is the bisector of the angle formed by L1 and L2. Given that L3 has a positive gradient, determine an equation for L3. Ooh. So let's do a little sketch. Might be the easiest way. I don't know if we do the axes actually. So we've got one line that's got a gradient of a half. So something like that. And one line with a gradient of 2. Something like that. And then our new line, L3, is going to come out over here like this. Somewhere in between. Where these two angles should be the same. So to do that, we need to kind of find those angles. So we can find the entire angle between the two lines. Then we can find half that angle, add it on, and then transform back into a gradient. This point was point C that we found as well. That's the 0.25. Which one was steeper? L1 was steep, wasn't it? Yeah, that's L1, that's L2, and that's L3. So, yeah, how do I actually find the angle from this? Well, let's just think about it in general. Let's look at L1. You'd have a line going up there, and then you can have the x-axis as well. So if we were to find the angle between the x-axis and the line L1, you can do SOHCAHTOA and think what's exactly going on. The gradient tells us that if we have 1 here, we have m over there. So we want to find the angle of that like right angle triangle. So you think we've got the opposite, we've got the adjacent. We know that tan of that angle in there is going to equal the gradient. So the angle it's at is the inverse tan of the gradient. So this is always true for every line. That's always how you can find how the angle compared to the x-axis. So we're going to use this now for both L1 and L2. And you can actually see if we just do like L1 would come down to here, say, L2 would be, L1 would come to here, L2 would be this. So if we just do the difference in them, that will give us then the difference in the angles in there. So if we call this theta, this is also theta because L3 is a bisector. So 2 theta is the inverse tan of the difference of the gradients, or the inverse tan of each gradient with the difference of them. So subbing that in the calculator, what do we end up getting? Inverse tan of 2, take away inverse tan of 0.5. We get 36.9, we'll call it. So yeah, let's call it 37, be easier to work with. And then theta will be half of that number, so 18.5. So that's the angle for this part. We then want to actually find like the angle of L3. So we do need to know what was the angle down here for L2. That was tan inverse of a half. So we can find out what theta plus alpha is. 18.5 plus the inverse tan of a half again. So sticking that all in, 18.5 plus inverse tan of 0.5, we get that it's 45. I imagine that if you did all no rounding, it'd be exactly 45. I am just above it here, 45.065. But yeah, we'll call it 45 degrees, nice and straightforward. So in that case, we can go back and think that the gradient of line 3, if I actually just get myself some more space a sec. Yeah, imagine the gradient of line 3, if it's a 45 degree angle, the gradient's 1. But we can find that using the gradient is going to be tan of 45. Yeah, that's equal to 1. So we know y is equal to x plus c, and it must go through our 0.25. So we can then do 5 is equal to x, which is 2, plus the c. C must therefore be 3. So the final answer for L3, y is equal to x plus 3. Lovely jubbly. Yeah, similar equation for that. Imagine if we didn't do any rounding, that should be completely fine. Let's double check that quick, just to see if there was some error I made. So if I actually don't take the answers here, let's go back up. I'm just going to do it in blue next to it. So 2 theta is, yeah, tan inverse of 2. Take away tan inverse of a half. Alpha is tan inverse of a half. And we need to find theta plus alpha. So half of this plus this. So half of tan 2, or tan inverse of 2. And then adding on half of this and half of this. Half of this and a whole one of this. So you've got this thing take away half of itself. So it's just half of it left over. So you can capitalize the half out. It's half of these things. So the tan of both of the gradients that we just had added together. That's going to be theta plus alpha. We then want to do tan of that. So tan of all of this stuff. I will expand those brackets actually. Let's try and write this a little bit neater. So inverse tan of tan 2, tan inverse 2. Move the other way. Plus inverse tan of a half, and again we need a half on there, which is where I've expanded that bracket, so half on that one, half on that one. Here then, I would guess you need to use the tan double angle formula. I don't know off the top of my head, let me just Google that. So tan of a plus b, what do we get? It's tan a tan b. Annoyingly with the half here, can we take the half out of the tan? I don't think we can. So I think there's going to be some not very nice things popping out. So we're going to have to, yeah, tan of the half of tan minus 1 or 2 plus, I've got no more space here. No, I've got no more space really. Plus tan half tan inverse of a half all over the product of them. Yeah, 1 minus those two things times together. So 1 minus tan of a half tan inverse of 2 plus, sorry, not plus, times tan of a half tan inverse of a half. So not very nice. I think there's probably some more expansion you could do here to get it out exactly. But I think with just the 5 marks, that's going to be a bit long-winded compared to what it should be. And we don't really learn too much about like half formulas and things like that in A-level maths. So that should be fine, I think. Like we get the number out, like this was so close to 45, I'd assume it's just going to be 45 and everything here. It was such a nice answer. It's most likely correct. And this seems, yeah, for 5 marks seems way too long-winded to be slogging yourself through. So hopefully that's all good. We'll double check all the answers at the end when I've finished all the questions. But yeah, it looks like it should be fine for me. So yeah, we get nice numbers by doing rounded. So this must be close enough, do you know what I mean, to give us the right thing. So we'll keep going. Number 11, we have some binomial looking thing, 1 plus 2x to the 7. We want to find the first 4 terms in ascending powers of x in the binomial expansion. Okay, so what's going to happen? Our power of x will keep increasing. We'll go from x0. Well, in this case, we've got 2x. So not just x0, but 2x to the 0, 2x to the 1, 2x to the 2, 2x cubed, and 2x to the 4. The other ones just have a 1 in them. So this would be like 1 to the 7, 1 to the 6, 1 to the 5, etc., etc. But the ones, no matter what power of 1 we have, it's just 1. So we don't need to bother writing them in there. The other bits we need then are the coefficients, where we're going to have 7 choose r, where r is like 0, 1, 2, 3. You can also get that from Pascal's triangle. 1, 7. Don't know actually what the Pascal's triangle for 7 is. We could figure it out though by using, so I know 1, 5, 10, 10, 1 is the row for 5. So for 6, it's 1, 6, and then 5 plus 10 is 15. 10 and 10 makes 20. 10 and 5 makes 15, then a 6 and a 1. So we have 1, 7, 21, 35, 35, 21, 7, and 1 again. So this row are the coefficients. Like imagine we went to 5, 6, 7, they'd be all the coefficients. Obviously, we've only got the first 5 of them. So it should be 1 times the first one, 7 times that stuff, 21 times that stuff, 35 times that stuff, and 35 times that stuff. So let's expand all those bits out. 2x to the 0 is just 1. 7 times 2x is going to give us 14x. I need it all added together. 2 squared is 4 times 21 gives us 84x squared. 2 cubed is 8. 8 times 35 is some number I don't think I can do in my head. 8 times 35, 280 x cubed. And then 16 times 35. So this is 1 more 2 than above. So it should be 560 by the looks of things. So 560 x to the 4. And yeah, this should be the first 4 terms in ascending powers of x in the binomial expansion of this lovely thing. So that's all good. Looking at part B then, let me just move my blue box up a little bit. Hence or otherwise, so and it says otherwise, don't do the otherwise. Always do use what you've done up here. Find the first 4 terms in the expansion of this thing. So we want to use just like the first 4 terms that we found above. Oh, this is 6 though. Okay. So we need to be a little bit smart. That's one thing to spot. Yeah, this said 7, this said 6. I'm hoping that's not a typo. And because these papers aren't like official papers, they're just ones that someone else has made, but they are very useful. So what we can actually do is kind of, we want to make that a 7. So if we add 1 power there, we can divide by 1 over here maybe. Yeah, I think that might be 1. So actually, what I'm thinking, has this got 1 plus 2x as a factor? We can check that. 1 plus 2x would give us a root of x is minus a half. So let's just sub in minus a half into there. Do we get 0? If so, then we can factorize with a 1 plus 2x. So doing that, we'll have 3. 4 times minus a half minus 2. And then minus a half squared is positive a quarter. Times by 4 is positive 1. Times by the negative is negative 1. So this does give us 0. So that tells us 1 plus 2x is a root of this quadratic. Lovely. So we can actually factorise that out. This quadratic, like I say, should have a 1 plus 2x. We still have the 1 plus 2x to the 6 here. And then on this side, what do we need? Well, to make this 3, we would need a 3. Like 1 times 3 must be 3. And to make this minus 4x squared, I need a minus 2 and an x. So minus 2x in there. This then, we can group these two together to give us the power of 7 that we had in part A. So 3 minus 2x times by the 1 plus 2x to the 7. And then, yeah, this thing is exactly this thing. And we've already found the expansion of the first 4 terms. We only need the first 4 terms in the next one. So we can think about basically having that 3 minus 2x times by our expansion. I will be lazy and just copy the expansion over like this. Duplicate. So in there it goes. We don't need the blue bit with us though. And then we can be a little bit smart about some of these things. Here, annoyingly, not much cancels out. Every single term here either has been times by a constant, so we'll have the same power of x, or it's been times by some multiple of x, so we'll increase by 1. So the only one that we can ignore is like the 560x to the 4 times by the 2x. Everything else we still need to calculate. But the way I'll do it is I'll go through the powers of x one by one. So for constants, what do we get is the 3 and the 1. For x's, we can have the 3 and the 14 is 42. Take away 2, 40. For the squareds, we'll have 3 times 84. When I'm getting these size numbers, I'll start using my calculator. So 3 times 84, where do the squares come from the other way? 2 and 14 is 28. So take away the 28 because it's negative. So we get 224. Lots of x squared. For the cubes, we'll have 3 and 280. So 3 times 280. And then this minus 2 and this 84. So minus 2 times 84 is 672. 672. Lots of x cubed. And then the last one, we have the constant and the x to the 4. So 3 times 560. And then we can also have the minus 2x and the 280. So take away 2 times 280. I think that's a 0. Oh, no, it's not 0. I'd be silly me. It is 1,120. I thought it was 0 because this was just double this one. But I forgot about the 3. That many x to the 4s. And that's all positive. So that should be final answer. So yeah, a bit long-winded, bit sneaky. We also did x to the 7, and this was x to the 6. So yeah, always be careful. Does the thing in part B actually match up with exactly what you had in part A? If not, that told us that, okay, hopefully then, because we've got 6 here, we need one more of them. Hopefully it's one of the brackets in there, and it was. So we subbed in 0 to show, subbed in the minus a half to show that this was 0, and therefore 1 plus 2x was one of the factors. Find the other factor, and then use that factor with our original expansion to expand it even further. Lovely jubbly. So on to number 12, which I think is the last question on the paper. So what have we got? A population of an endangered species of animal was introduced to a park. Population obeys this equation. Oh, lovely. So whenever you see something this horrendous looking, generally the question itself isn't too bad. Normally they did make it look scary, but the actual solving of it is okay. K and A are positive constants. T is time in years, since the species was introduced to the park. Initially 100 animals were introduced to the park, and this population doubled after 5 years. So that K equals 8. Okay, so we've got 2 coordinates. If we think about having like time and population as our pair of coordinates, we had 0 and 100. They started with 100. And after 5 years, it's doubled to 200. So we have these 2 different coordinates. Let's just sub them into our expression. And what we should see, because we only had 2 constants, and we've got 2 different coordinates, we get 2 equations, and then we can solve them simultaneously for our 2 constants. So doing the first one, the t being 0 is quite nice, because then all the powers of 0 are going to go away. So we'll have 100 is equal to 125, k, a to the 0, which is just 1, don't need to put that in there, over k plus 2a to the 0, a to the 0 again, just being 1, so just plus 2. So this one, we can actually just solve for k straight away. So you can see this part, we didn't need to find a. So solving them simultaneously solves a and b together. So if we times by k plus 2, we'll have 100k plus 200 is equal to 125k. And then slowly subtracting this, 200 will give us 25k on this side. And then, yeah, k is equal to 8. So that's a good sign. Always a good sign when they show that it's exactly the answer that you get at the end. Find the value of a. So now we need to use that second coordinate, the 5 and the 200 we have. So let's sub those in. What does that give us? 200 is equal to 125 times by the k now. So that's 1,000. We can just put that in straight away. A to the power of t, which in this case is 5, over k, which was the 8, plus 2a to the 5. So similar process. Let's times by the denominator. We'll have the 2 times the 8, so 200 times the 8, so 1,600. The 200 times the 2a, so the 400 lots of a to the 5, and that will equal to 1,000 a to the 5. Let's take all the a to the 5 to one side, so we'll have 600 on the right, is equal to 1,600. So a to the 5, if we divide by 600 there, we will have 16 over 6, which is going to be 8 over 3. So a should be the 5th root of a over 3. Let's look in the calculator, see what number that gives us. So we need 8 over 3, all to the power of 0.2, or 1/5. Gives us 1, how many significant? 4 significant figures. So 1.217. Obviously this does keep going, it's just like a never-ending decimal. But like I say, we only needed 4 sig figs here, so that should be all good for the answer. Now then, find the value of t when p is 400. So we have all the constants, we have k and a. So we just want to take this expression and sub in the 400, the a and the k. So p is 400, equal to 125 times the k was 1,000, just like last time. And this a number is not very nice, so we'll actually just keep calling this a, and then slowly we'll just rearrange for a to the t, and then solve that for t at the end. K was 8 again, plus 2a to the t again. And let's just rearrange. So similar sort of idea. 400 times the 8, as we multiply by the denominator, will be 3,200. And then 400 times 2 is 800. So 800 a to the t. It's equal to 1,000 a to the t. Take all the a to the t's to one side. 3,200 will equal to 200 a to the t. And then as we divide by 200, we will get that a to the t is equal to 16. So to find t then, we need to do the log of a of both sides to get the 16 to pop out. This then is probably not a very nice number. Obviously our a was 1.217. So let's sub that in there. What do we end up with? So log base 1.217 of 16 gives us 14.1, we'll call it. So yeah, 14 years it took to hit, hit 400, which kind of makes sense. We start with 100, doubled in 5 years. Well, you can think, yeah, you've gained 100 in 5 years. You've gained another, like in another 10 years, you've gained another 200. So it's almost not like it's not an exponential growth they're experiencing here. It's not linear, obviously look at it's like a not linear thing, but it's not exponential. And looking at part D, why can this not exceed 500? Tells us already it's not exponential, because we're not going to be seeing, like, there would be no maximum if the function was exponential. So why can it not exceed the 500? Let's just go and plug in the bits that we have. So we knew like the k was 8, wasn't it? So it's 1,000 when it's times by 125. A to the t over the 8 plus 2a to the t. So what's going to happen, basically, when you're thinking about like as t goes to infinity, this would go to infinity, so it's not going to work. So we're thinking about the limit of this function. How you want to deal with limits in this sort of scenario? Divide by the horrible bit. So we'll have just 1,000 on the top. The 8 now on the bottom will be 8a to the minus t plus 2. This then is nice and easy to calculate when it tends to infinity. So if t goes to infinity, a to the minus t goes to 0. So yeah, t goes to infinity. That tells us that a to the minus t goes to 0. So 8 times that still goes to 0 as well. If we add 2 to that, it's going to go to 2. And 1,000 obviously goes to 1,000. It's going to stay where it is. So we end up being, it's the whole thing, p is going to tend to 1,000 over 2, which is 500. This is a way, I don't know if you get taught this at school, but when I was at university, like the first, I think it was the first year, yeah, like real analysis, when you're talking about limits and like as things tend to infinity or minus infinity, if you've got something that looks like it's going to tend to infinity, you just divide by the highest power, or like the power that's the most disgusting. So for example, if we had something like x to the 4, let's say 3x to the 4 over 2x to the 7, what that's going to tend to is going to be 0. But if we actually do it slightly differently and have it to be like x to the 4 here, plus 6 and like plus x squared or something, you would divide top and bottom by the highest power. So this would be 3 plus 6x to the 4, sorry, 6x to the minus 4, over 2 plus x to the minus 2. Both of these parts would go to 0, and you're left with just the 3 over 2. So that's the way we deal with limits when you've got like fractions of polynomials or fractions of like functions that are not very nice. Look at the most horrible bit, in this case our a to the t, and just divide by that, so it becomes negative t and tends to 0. Another way, like think of everything that tends to infinity. You want that on the bottom of the fraction. You don't want it on the top of the fraction. So that was the last one. So let's get up the mark scheme, and we'll just double check that everything was correct. But I don't think I made any mistakes. Yeah, the last 2 days I was doing it like streaming for the first time, a little bit. Not, well, I suppose nervous is the right word, isn't it? How do we get back to the actual paper itself? There we go. This is C solutions. But yeah, last couple of days I made a few mistakes. Did rectify them, but yeah, a few mistakes as we went through. Let's just double check everything here is correct. So, page 1, we needed 21. Yeah, that's all good. Page 2, we needed to have, our graph looks good. We got 4, a half, and 4. We had the right solutions at the very end. So yeah, generally if you've got the right solution for the last part of the question, most likely you've got the right solution everywhere else. Like you couldn't have really gone through and got like, this is wrong, 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 wrong. Oh look, you got everything right at the end. It doesn't really happen that way. You end up just like all right. If the end one is right, most likely all the rest of them are correct as well. Number 3 then. Oh, wait, we're good. Number 3. We had 10 for an answer. Yeah, 10 was good. We got to show that. And we found it was a minimum. Yeah, showed it was a minimum. Nice and easy for that. Show that. Number 5. We should have 3 through 5. Or if I skip 4. Yeah, I skipped 4. 3 through 5. Sorry, 3, 5, 5. Oh, did I get that wrong? Have I just done the maths wrong? So yeah, it should be 1065 divided by 3. 355, yeah. So I think I just need to rewrite that one. That should be a 5 in there. 5. Go back to blue. 415, 475. That's all spot on. We'll keep going. Part B. Centre was 3. Oh, they had 3, 3. Radius 5. Okay. I didn't get 3, 3. Let's double check then what's gone wrong. So let's get this back into full screen. So we're looking for 3, 3. The number looked quite nice, like yeah, 7 halves. So it should be 6 halves. Have I just done like a slight error that's just a little bit wrong? That's 4. So what we had here, we had 3 points on the edge of a circle, and we needed to find the centre of the circle. This was -1, this was 7, this was the 3, 8 we're told at the top here. So the way that this works, you find the lines that join them up. You could do this one as well, you only need 2 of them. And then it's the midpoints and the normals at those midpoints where they intersect. So let's go through and just check all the maths we've done. You can see lots of little calculations have been done on this page, so any one of those being incorrect will kind of cascade through and change everything else going forward. Sometimes it's easy to work backwards. Obviously, we can kind of like all this radius stuff is definitely wrong because we've used the incorrect radius up there. So we can just rub all of that out. That's definitely all wrong. But let's have a look, try and backtrack to what was actually incorrect. So we're looking for 3, 3. The x was 3 already. We got that quite early on because we found the midpoint of this was 3. This was a flat line, like it's horizontal. So the normal is perpendicular. So we had to have the centre on the line 3, without a doubt. And from there then, what do we need to do? So let's see if we can go from the start. So line AB. So A was -1, 0. And that was 8, 3. So yeah, 8 take away 0. And 3 take away -1, 3 plus 1. 8 over 4 is 2. So we've got y equals 2x plus c for this line. Plugging it in the coordinates of -1 and 0. 0 would be -1 times 2 is -1, plus a c, so c is 2. So I think this is all good. So we'll kind of put like red squares around what I think is good now. Finding the midpoint then, we did the average of the points. So we had 0 and 8 gives us 4, -1 and 3 does give us 1 in the middle. So that looks good as well. That seems fine. Yeah, that seems good. So that's that line. We then need the line L2 that I've labelled here, this kind of decreasing line. So we knew line AC had a gradient of 2. These must be perpendicular. So we need to have a gradient of -0.5. Again, don't know the plus c. But then we use the coordinates of 1, 4. Yeah, so okay. This had -0.5 times x. X is 1. So I've done 1/2 times 1 and got 1. So you can see how it just takes one little math error to like kind of cascade through. But like I say, nothing, if you make little errors, there's no harm done. You can always just kind of backtrack and double check when you've got the time in the end. So we do get 2 hours this exam, up in what? An hour and a quarter. So you'd have 45 minutes in the exam to double check all this sort of stuff. So let's propagate this through. This means that C actually is not 5, but 4.5, which is 9 over 2. So we can put that in here as well, 9 over 2. Where did we use that going forward? So now we had L2 and L1. We needed the point of intersection. L1 was just nice and simple. The line x is 3. So let's plug in 3 into there. And what we'd see, this part will be the same. -1/2 of 3 is -3/2. But now we have plus the 9 over 2. And we can see, yeah, so we were only 1/2 off. This changed by 1/2. So this now does become 3. So we've got the centre of 3, 3, just as the answers now say. Last part then, just to find the radius. So for that, we want to find the distance between the centre and any of our points A, B or C. We'll use B, nice and straightforward. It's got a 0 already. So we know that like kind of the vector there is going to be something, like the y coordinate is going to be -3, the difference in them. And how much across does it go? Well, it goes from 3 to 7. So it goes across 4. So to do that now, what we've kind of shown, we've got like a right angle triangle. This is 3, this is 4, this must be 5, like Pythagorean triple. We can show that quick with the Pythagorean theorem though. So the 3 squared, or -3 I suppose, all squared, plus the 4 squared gives us altogether 25, and that would then be equal to r squared. So r is √25, which is 5. Lovely jubbly. So yeah, not too bad to recheck. Like I say, in the exams, always just go through and double check everything is actually correct. A way you could have checked that, obviously without the answers, is a circle. So all the points should be equal distance from the centre. So as we did like the double check, we should be should have the same distance between like A in the centre, C in the centre, and B in the centre. Also, the actual number that we got, like in the incorrect way, was 113 square rooted over 2. We should really be thinking like, that's not very nice. Everything else on the page is a whole number. We've not even, or like a fraction of a half, do you know what I mean? But they're all quite nice numbers. Compared to this thing is not very nice at all. So when you get out an answer that does look kind of horrendous compared to everything else, it's not a sign that you're wrong, but it's an indication that maybe something did go incorrect. So it's just worth like, if I was retaking the exam I'd put extra careful, like extra special interest into this number and thinking, is that definitely correct? So it's not a sign that you're wrong, but it's where I'd first start looking for something that is wrong. So we'll rub that out so I don't think about it in the future. Let's get those answers back up. So yeah, raised to 5, lovely, jubbly. So yeah, they did it a different way, I think. Have they? Yeah, I think they did it a slightly different way to me. Or there might be many ways to do it. So question 6, what should we get? -4 over 3 and 0, and a scale factor of 16, or enlargement, yeah, it was a vertical enlargement, so 0, 16 as a vector. That's all good. For number 7, oh, this is a proof. Yeah, the proof is not too bad. Just a case of like showing things are multiples of 3. We end up with something like everything's got a factor of 3 at the front. Do you mean like this over here? And we did it by exhaustion. So looking at what the question said, prove by exhaustion that if n is a positive integer, that is not divisible by 3. So for exhaustion, you try all the cases. Often you think of this as being like try all the numbers. But if something's not divisible by 3, either it's 1 more or 1 less. So we just did that with the n squared minus 1 and showed they're all multiples of 3. I did it a little bit sneaky, did plus or minus 1 and propagated that through. But it still ends up mathematically the same as if you did them separately. So keep going. Question number 8. It's that. Okay, yeah, it's thousands. They asked for the initial value. I forgot it's in thousands. So this 40, it should actually be 40,000 in there. So I think a few other things. If there's any other value formulas, yeah, this value answer where we've got that 113.58, that should be thousands. So it should be 113,580-ish. Imagine that was rounded already. Back to red. Everything else looking fine. Yeah, just plot the straight line graph, plotting that up there. C was roughly 11%. Yep, that's good. 114. Okay, so they rounded up to 114,000. But yeah, that's all spot on. Question 9. That was just a derivation. Do the whole format, so nothing to even really check there. That's all just, it's like a show that, do you know what I mean? We got to the right answer, so we know that we're correct on that one. Yeah, this one, I imagine, have they done it with tan on here for question 10? There's some weird, you can see like I rounded numbers, and then I got like the angle was 45.02 or something, which is basically 45. And if you use 45, you get a nice solution of x plus 3. Do we get that same solution for the answer? Yeah, y equals x plus 3. I'm guessing they went and did some stuff similar to what I've done. Yeah, so I think because we got that last answer right, hopefully everything else is okay. Bit of a weird question, it's not one I've seen before. Where you basically have the idea of like, we had two lines, L1 and L2. We wanted to find the equation of their bisector. So we used the fact that if you had like the angle between a line and the x-axis, you can find that by doing inverse tan. I don't know if I left it. Yeah, I've left the drawing down here. So yeah, any line that you'd have, you can think of like a right angle triangle. You could draw with that, where the line is hypotenuse. You take an m steps up for every 1 step to the right. That should be 1, not 11. So you've got the opposite, you've got the adjacent, and tan then is opposite over adjacent. So tan of the angle of a curve is always just the gradient. So you can find the gradient or find the angle by doing inverse tan of that gradient. So we did that, plug for everything. And like I said, I think there's a way you could do it exact, which is what I start to show in this blue bit. But I was like, yeah, this seems too much work for 5 marks. It seems too long-winded and too kind of horrible. That's a good sign as well. If you start doing something, it's like, this is a slog. This just seems like so much effort for such a little amount of reward. You don't need to be doing it. There's probably an easier, simpler way of doing things. And here they did just kind of allow you to round everything and work with that. So hopefully that's not too bad. Unless they've done like some other random stuff to get the answers out. Yeah, they might have done some other little steps. So how do they actually do it? Find a point on D. BC. Okay, so they're finding like a equal distance. Okay. So we knew where point B was, and they're trying to find point D on the second line. Find the gradient from and then it's the midpoint. Okay. So yeah, they find the midpoint of that. So where I had this diagram here, if I move this down a little bit. We had this diagram. We knew like a point here. They're saying find another point here so that like this gap and this gap are the same length. you can then find the midpoint, and that then should be on that middle line. That's a little bit easier than what I did using tan of the angle and stuff. But everything, well, maybe not everything, but a lot of these questions will have multiple ways of solving it. Like I say, yeah, this, we could have chugged through and got the exact value, but enough rounding here, we kind of assume the rounding is all going to cancel itself out, which it did in the case. So we'll keep going. Question number 11. Binomial expansion. Did we get everything right? What do we get at the end? 3, 40, 224, 6, 7, 2. Yeah, good. Did I actually ask for only... the first 4 terms. So I've done extra work here. I did up to power 4. So I could have saved myself a little bit of work there. But hey, if you do more work, that's no harm done. You have still found like the first 4 of them, do you know what I mean? Even though you've done extra stuff. If I found the whole thing, I've still found the first 4. So yeah, no harm done there. Just wasted a little bit of time in the exam. We'll go number 12 then, last question. 14.1 for the last answer. 14.13, yeah, lovely. So we'll put that 3 back in there. So yeah, obviously, if we get the last question right, most likely we've got everything else correct. We will just double check. So A, yeah, 1.127. Sorry, B, well, question B, A was equal to 1.217. And yeah, K was 8, that was a show that. The part D was like, why is it going to end up at 500? That was this massive limit at the top that we did. So we had this kind of horrendous looking function. A to the t, a was a number bigger than 1. So as t goes to infinity, a is going to be like you're timesing together 1.127, multiple times. It's going to keep increasing. So this would tend to infinity. We don't really want that. So what you do is you take the stuff that's going to tend to infinity, and generally the bits that are going to do it fastest. So for example, a to the t would go faster, like 2 to the x goes up faster than x squared. The exponential beats out the power of 2. So we divide by the fastest increasing thing. In this case, it's the same. It's just a to the t. So where these 2 terms had it, this one didn't. The 2 that had it lose it, and the one that didn't gets a minus a to the t, or a to the minus t. That's useful because we knew that a to the t goes to infinity. So 1 over a to the t goes to 1 over infinity, which is 0. That's not the right way to write it down. It just tends to 0. So what we can do is then sub in 0 for that value. And what we see is you get like just 1,000 over 2, which is what I'm kind of showing down here. So lovely. That's all, yeah, all correct. All good. All full marks. Just that one bit of me doing 2 times 1 and getting, 1 times a half and getting 1. So you see how it's sometimes just take one little error can be the only thing you get wrong in the exam. But any questions about any of these bits, give me a shout in the comments. If not, thank you very much for watching. I'm going to keep going through all of these. So yeah, this is paper C. There is, alphabet-wise, there is 26 of them. If I go back on this page, yeah, 26 of them. I'm not going to do one every day. I don't know exactly when I'll do the next one, whenever I feel like it, basically. But yeah, over time, I will put all these up there. So anybody doing A-level maths or any kind of equivalent, so if you're in, I suppose 18 years old is when these exams get done. These ones that we've been doing they feel like a little bit earlier. Maybe these are the 17 ones. But as we get towards the end, they will be much more difficult. So we'll do all of them. So hopefully anyone that's watching is finding these quite helpful. But like I say, yeah, any questions, put them in the comments. If not, thank you very much. And I will hopefully see you on the next one that I do. Right. Cheers. Bye.